Every detail in this story comes from real scientific research and observation. There is a mountain on Mars that is so large you cannot see its peak from its base. Not because of clouds, not because of distance, because the curvature of the planet curves away before your eyes can reach the summit. The mountain rises 21.9 kilometers above the surrounding plains. That is 2.5 times the height of Mount Everest above sea level, and it is sitting there right now on a world 225 million kilometers from where you are lying. There is a canyon on Mars that stretches 4,000 kilometers from one end to the other. If you placed it across the United States, it would run from the Pacific coast to the Atlantic. It is 200 kilometers wide in places. It is 7 kilometers deep. The entire Grand Canyon could fit inside one of its side branches, and you would have to look carefully to find it. There is a machine on Mars right now, a machine built by human hands, crawling across a dry riverbed that has not carried water in 3 billion years. Its wheels are pressing into dust that was last disturbed by flowing liquid before complex life existed on Earth. Every few seconds, it takes a photograph. Every few seconds, it records the temperature, the wind speed, the composition of the air. It does not know you are listening. It does not know anything. It simply moves. The sky above it is the color of a bruised peach at noon. At sunrise, that sky turns briefly, impossibly blue. Not for long. Within minutes, the suspended iron oxide dust catches the low angle of light, and the blue fades back into the familiar pale butterscotch that has covered Mars for hundreds of millions of years. The dust itself is extraordinary. Individual particles average 0.6 micrometers in diameter, small enough to stay suspended in an atmosphere that is 170 times thinner than the one above your head. These particles do not fall the way dust falls on Earth. They drift. They float on the edge of nothing for months. In 2018, a dust storm grew until it covered the entire planet. Not a region, the entire planet. Every surface, every canyon wall, every volcanic slope, buried under a sky so thick with dust that solar-powered machines lost contact with Earth and never woke up again. That storm has passed. Others are coming. There is a helicopter on Mars that was designed to fly 5 times. It flew 72. On its 72nd flight, it landed on uneven ground and never flew again. It is still there, tilted slightly, alone, 700 meters from the rover that carried it across 160 million kilometers of space. There is a valley on Mars where the walls drop so fast and so far that standing at the rim, you are looking down at a floor that exists in a completely different climate zone. The bottom of Valles Marineris is warmer, denser, more sheltered from the wind. It has its own weather. Dust devils that form in its depths never reach the rim. The canyon is so deep, it has an interior. There is a volcanic shield on Mars so wide that if you were standing at its center, you would not know you were on a mountain. The slopes rise less than 1 degree. You would walk for 300 kilometers before you began to feel the incline. The summit caldera is 80 kilometers across. The entire city of Los Angeles could sit inside it with room to spare. There are sealed metal tubes sitting in the Martian dust right now, each one the diameter of a pencil, each one containing a core of rock drilled from an ancient lakebed. They are waiting for a mission that has not launched yet. When it does, and if it succeeds, those tubes will be the first material from another planet ever returned to Earth for laboratory analysis. The answers inside them, if there are answers, will take decades to fully understand. There is a place on Mars where the sun sets in the east, not because the planet rotates differently, because you are standing deep inside a canyon so wide that the western wall blocks the western horizon entirely, and the only sky you can see is above and to the east. Sunrise and sunset are reversed by geography alone. There is a region on Mars called the Métis-Fossé Formation, a deposit of material so light, so porous, that radar signals pass through it almost without reflection. Scientists have debated for decades what it is made of. Volcanic ash, dust, ice. The debate is not settled. Something enormous was deposited there, covering an area larger than India, and no one is entirely certain what it was or where it came from. And somewhere in the middle of all of this, the mountains, the canyons, the ancient riverbeds, the quiet machines, the butterscotch sky, something might still be alive. No one knows. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail you will hear tonight is drawn from real missions, real measurements, and real planetary science published by researchers currently studying Mars. Just relax and feel free to let this play as you drift off to sleep. Now, let us go to Mars. Mars is the fourth planet from the Sun, orbiting at an average distance of 227.9 million kilometers. A Martian day, called a sol, lasts 24 hours, 37 minutes, and 22 seconds, only slightly longer than a day on Earth. But the similarities end quickly. The atmosphere of Mars is composed of 95.3% carbon dioxide, with average surface pressure of approximately 600 pascals, less than 1% of Earth's atmospheric pressure at sea level. The average surface temperature is -60 degrees Celsius, with swings from -125 degrees Celsius near the poles in winter to as warm as 20 degrees Celsius near the equator on a summer afternoon. Mars has no global magnetic field. It has no liquid water on its surface. What it does have is a geological record stretching back 4.5 billion years, currently being read, one rock sample at a time, by a six-wheeled vehicle the size of a small car. That vehicle landed in Jezero Crater on the 18th of February, 2021. It is still there. It is moving right now. Tonight, you are on the surface of Mars with it. You are standing at the western edge of Jezero Crater, and the ground beneath your feet is not sand. It looks like sand from a distance. From orbit, it looks like the floor of an ancient lake, which is exactly what it is. But standing here looking down, you can see that the surface is a layered thing, compressed sediment pressed into thin horizontal bands, each band representing a different period in Mars's history, the way tree rings carry years inside them. The layers are reddish-brown and pale tan, and in some places a surprising gray. The gray is olivine-rich basalt, the original volcanic floor of this crater, exposed where wind has stripped away the sediment above it. The crater itself is 45 kilometers wide. It formed approximately 3.9 billion years ago during a period of intense bombardment when the inner solar system was still crowded with leftover debris from planetary formation. The impact that created Jezero was large enough to punch through the Martian crust and expose deep rock from below. Then, over hundreds of millions of years, water filled it. Not once, but in multiple episodes. Jezero held a lake that was, at its deepest, roughly 250 meters of standing water. Rivers fed it from the northwest and the southwest. One river built a delta, a fan-shaped deposit of sediment that is still visible from orbit today, preserved in the rock like a photograph taken 3.5 billion years ago. You're standing on that delta. The rock beneath you was once the floor of a river mouth. These sediments were carried here by moving water, grain by grain, dropped when the current slowed as it entered the lake. Geologists on Earth can read the structure of that delta and reconstruct the speed of the water, the depth of the lake, the duration of flow. They have done exactly that. The river that built this delta flowed for at least a few 100,000 years, possibly much longer. 3.5 billion years of stillness. The wind moves now. You can hear it, or rather, you would hear it if you were here, though the sound would be faint. The Martian atmosphere is so thin that even a wind moving at 30 meters per second sounds quieter than a light breeze on Earth. The sound waves travel differently in this air. The speed of sound on Mars is approximately 240 meters per second, compared to 343 meters per second on Earth. High-frequency sounds, anything above a few hundred hertz, are absorbed more quickly by the carbon dioxide atmosphere. Lower frequencies carry farther. The world here is not silent, but it sounds muffled and distant and very old. The dust moves around the base of the rocks near you. These rocks are not random. They have been named. Perseverance's science team assigns informal names to geological targets before the rover approaches them, a tradition borrowed from Mars exploration going back to the Pathfinder mission in 1997. The rocks here in Jezero's Delta region have names drawn from river systems on Earth, names from rivers in South America, Africa, the western United States. Scientists on Earth argued for weeks about which rocks to approach, which to drill, which to leave behind. Time on Mars is limited. The rover's power supply is a multi-mission radioisotope thermoelectric generator, a device that converts heat from the radioactive decay of plutonium-238 into electricity. It produces approximately 110 watts of electrical power. That is less than 2 standard incandescent light bulbs. It is enough to run everything aboard the rover, every instrument, every wheel motor, every radio transmitter, for the entire duration of the mission. 110 watts, crawling across a world. Perseverance carries 7 primary scientific instruments. The one working hardest right now is Mastcam-Z, a pair of zoomable cameras mounted on the rover's mast at a height of approximately 2 meters above the ground, roughly eye level for a standing human. Mastcam-Z captures stereo images in multiple wavelengths, including ultraviolet and near-infrared, which are invisible to the human eye but reveal information about mineral composition. The cameras have a resolution of 1,600 by 1,200 pixels and can zoom up to 26 times optical magnification. When the science team back at the Jet Propulsion Laboratory in Pasadena wants to look at a rock ledge 300 meters away, they zoom in with Mastcam-Z and read the geological record from a distance before committing the rover to the drive. Every image Mastcam-Z captures must be compressed and transmitted to Earth. That transmission does not go directly. Perseverance sends its data to one of 3 relay orbiters, Mars Reconnaissance Orbiter, Mars Odyssey, or the European Space Agency's Trace Gas Orbiter, which then relay the data to the Deep Space Network, a system of large radio dish antennas located in California, Spain, and Australia. The round-trip light travel time between Mars and Earth at average distance is approximately 12.5 minutes. When the planets are closest, about 3 minutes. When they are farthest, about 22 minutes. There is no real-time communication. Every command sent from Earth arrives at Perseverance several minutes after it was sent, and every response from the rover arrives minutes after that. The rover navigates and makes many moment-to-moment decisions autonomously, using onboard hazard detection software to stop itself if its cameras identify a rock or slope that could damage it. It is in this way deeply alone, moving through a world where no signal arrives in time to save it, making its own small choices in the dust. The instrument called Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, is mounted on the rover's robotic arm. Sherlock uses ultraviolet Raman spectroscopy to detect organic molecules and minerals that may have formed in the presence of water. It is looking for the chemical fingerprints of life, not life itself, but the kinds of carbon-bearing molecules that biology tends to leave behind. Sherlock has detected organic molecules in Martian rock samples. This does not mean life has been found. Organic molecules can form through purely geological and chemical processes without any biological input. But it means the search is real. It means the rocks here contain the building blocks of the chemistry that life requires. Whether life ever assembled those building blocks into something self-replicating is the question that has not yet been answered. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, ran 16 test operations between 2021 and 2024 before being retired. Its purpose was simple: demonstrate that breathable oxygen could be extracted from the Martian atmosphere. MOXIE worked by electrochemically splitting carbon dioxide molecules, each containing one carbon atom and two oxygen atoms, into carbon monoxide and oxygen. In each successful run, MOXIE produced between 5 and 10 grams of oxygen per hour. A person at rest requires approximately 30 grams of oxygen per hour to breathe. MOXIE was a small prototype, barely the size of a car battery, but it proved the process works. A full-scale version of that technology, the kind that would be needed to support a human crew on Mars, would need to produce kilograms of oxygen per hour. Engineers now know it is possible. You are standing in the crater where that proof was assembled. The sky above you is changing color as the sun moves. Mars receives about 43% of the solar irradiance that Earth receives, because it is 1.5 times farther from the sun. The sun appears roughly 63% the diameter it appears from Earth. It is still bright enough to cast sharp shadows across the delta rocks, bright enough that unprotected human eyes would be damaged by its ultraviolet output in the absence of Mars's magnetic shielding. The planet has no global magnetic field to deflect the solar wind, that stream of charged particles constantly flowing outward from the sun. The Martian magnetosphere is only local and patchy, remnants of a global field that collapsed approximately 4 billion years ago when the planet's molten iron core cooled and solidified. Without that field, the solar wind reaches the upper atmosphere directly and has been stripping it away for billions of years. That is partly why the atmosphere is so thin today. The dust at your feet contains iron oxide, rust, in the most basic chemical sense, iron 3 oxide, Fe2O3. This compound gives Mars its distinctive red color, visible even from Earth with the naked eye. The redness is not uniform. Up close, the surface is a range of tones: dark basaltic gray where volcanic rock is exposed, pale cream and tan where fine dust has accumulated in wind shadows, rust orange on open plains where the iron oxide is densest. The dust is not simply colored rock. It is the product of 4 billion years of chemical weathering, of ultraviolet radiation breaking down iron-bearing minerals on a surface with no liquid water to wash them away, no plant roots to anchor the soil, no microbial mats to fix the chemistry. Every particle of dust here has been alone for an incomprehensible length of time. You look to the northwest, toward the fan of the ancient river delta, and the rock record is clear even from here. The layers tilt slightly. Geologists call this cross-bedding, a pattern formed when sediments were deposited by moving fluid at an angle to the main flow. You can read the current direction of a river that died 3 billion years before the first tree grew on Earth. The tilted layers say, the water came from there. It moved at approximately this velocity. It carried sediment of approximately this grain size. The delta spread across this area for at least this long. Perseverance has drilled into some of these layers and extracted rock cores roughly the diameter of a standard pencil and about 6 centimeters long. As of the most recent mission updates, the rover has collected more than 20 sample tubes, each sealed and deposited at designated cache sites on the Martian surface. These tubes are waiting. A future mission, currently planned as a joint NASA and European Space Agency operation, will land on Mars, retrieve the tubes, launch them into Mars orbit, and bring them to Earth. If that mission succeeds, those cores of ancient delta sediment will be studied in laboratories on Earth with instruments far more sensitive than anything a rover can carry. Scientists will look for isotopic signatures, for chemical gradients, for cellular structures preserved in silica. They will look for anything that could only have been made by something that was once alive. Those tubes are sitting in the Martian dust right now, sealed, waiting, perfectly still in a place where nothing has moved in 3 billion years except the wind and the dust. The wind picks up slightly, and you can see, not hear, only see, a small dust devil forming perhaps 2 kilometers to the east. Mars generates dust devils constantly, especially in the afternoon when the ground heats unevenly. A Martian dust devil can reach heights of 8 kilometers, far taller than any dust devil on Earth. They are not dangerous in the way tornadoes are dangerous. The atmosphere is too thin to carry significant force, but they are electrically active. The friction of dust particles moving past each other generates electrostatic charge, and a large Martian dust devil can produce electric fields of several thousand volts per meter. The dust devils also serve a function that surprised early mission planners. They clean solar panels. Several Mars rovers in the past, including Spirit and Opportunity, had their power restored unexpectedly when passing dust devils swept fine particles off their solar arrays. Perseverance does not rely on solar power, so this cleaning effect does not matter to it. But the dust devils still pass over it occasionally, and MEDA, the Mars Environmental Dynamics Analyzer, records every fluctuation in pressure, temperature, wind speed, and electric field as they do. The dust devil to the east has climbed to perhaps 1 kilometer now. It is moving slowly, roughly 4 meters per second. Inside it, individual dust grains are spinning at much higher speeds. The smallest grains, those under a few micrometers, are being lifted into the upper column and will stay suspended in the atmosphere for days, possibly weeks, before settling. Some of them will travel hundreds of kilometers before they land. Some of them, during global storm season, travel all the way around the planet. You watch it move across the crater floor and dissipate at the far wall, the dust dispersing back into the general haze. Near the base of the delta, there is a flat-topped ridge of rock roughly 4 meters high. Perseverance spent several weeks examining this feature, which the science team nicknamed Skinner Ridge. The rocks here are composed of materials that appear to have originated outside Jezero Crater, carried in by the ancient river, swept down from highland terrain to the northwest. Among the minerals identified in these rocks is carbonate, a mineral that forms in the presence of water and often preserves organic material. The presence of carbonates in a delta deposit is exactly the kind of geochemical context that astrobiologists had hoped to find when they chose Jezero as the landing site over dozens of other candidates. The choice was not simple. Jezero competed against more than 30 alternative landing sites during a multi-year selection process. Each site was evaluated for scientific value, landing safety, and drive accessibility. Some sites with higher scientific promise were rejected because the terrain was too rough for safe landing. Jezero was selected because it combined high scientific value, an ancient lake with a well-preserved delta, with a relatively flat landing ellipse. The rover had to land within a region roughly 77 by 18 kilometers, guided to a precise location using terrain relative navigation, a system that compared real-time camera images to stored maps of the surface during descent. Landing a 1,025-kilogram spacecraft on Mars using a sky crane, a rocket-powered hovering platform that lowered the rover on cables and then flew away to crash at a safe distance, with a signal delay of 11 minutes and 22 seconds, with no ability to intervene in real time from Earth. It landed, precisely, within the target zone. Ingenuity, the small helicopter that traveled to Mars attached to the belly of Perseverance, flew for the first time on April 19, 2021. It climbed 3 meters above the surface, hovered for 30 seconds, and landed, the first powered, controlled flight on another planet. Its rotor blades, 1.2 meters in diameter, spun at approximately 2,500 revolutions per minute to generate lift in an atmosphere that is roughly equivalent in density to Earth's atmosphere at an altitude of 34 kilometers. No aircraft on Earth operates at that altitude. The technical difficulty of flying in Martian air required blades that were much larger and spun much faster than anything needed on Earth to lift an equivalent mass. Ingenuity was designed for 5 flights. It completed 72. In its 72nd and final flight, on January 18, 2024, the helicopter suffered damage to one or more rotor blades during landing on uneven terrain. Communication with the helicopter was briefly interrupted. When contact was restored, telemetry confirmed the helicopter had sustained damage that prevented further flight. It is still on Mars. It will remain on Mars. It rests approximately 700 meters from where Perseverance is currently operating, tilted slightly on the rocky ground where it landed for the last time. 72 flights. Then stillness. The rocks in this part of the crater floor are coated in a thin layer of fine dust. If you were to run your gloved fingers across the surface of a rock here and stay with this, you would feel that the dust does not cling the way dust clings on Earth. The electrostatic properties of Martian dust are different. It adheres easily to smooth surfaces under certain conditions, as engineers discovered when designing dust mitigation strategies for solar panels. But on the rough surface of a basaltic rock, in low gravity, 0.378 of Earth's, The fine particles sit loosely, ready to be disturbed by any movement, by any breeze. Running your fingers across the rock would leave a mark, a swipe of darker gray where the dust cleared. That mark would remain for years, possibly centuries. There is nothing to erase it except the wind, which sometimes moves the fine dust back over a surface, and sometimes simply carries it somewhere else entirely. The light is changing. The sun is lower now, dropping toward the crater rim to the west. The shadows of the delta rocks are lengthening, stretching east across the layered floor. The color of the sky shifts almost imperceptibly, becoming slightly more orange, slightly more saturated with suspended dust, catching the oblique light. In approximately 40 minutes Martian time, the sun will set, and for a few minutes, the sky near the horizon will turn an unexpected color, blue. The blue of Martian sunset comes from the same dust that makes the daytime sky look orange. Fine iron oxide dust particles scatter blue wavelengths preferentially at low sun angles, the same principle that creates blue skies on Earth. In reverse, on Earth, molecules in a thick atmosphere scatter blue light in all directions, giving the whole sky a blue cast. On Mars, the thin atmosphere scatters less, but the suspended dust near the horizon performs a similar trick when the sun is low. For a brief period at sunrise and sunset, the sky near the sun turns a deep cold blue, then fades. It is one of the stranger things about this place. The colors here are never quite what intuition predicts. The daytime sky is not blue. The sunset is. The temperature is dropping faster now. Mars has no ocean to store heat, no thick atmosphere to insulate the surface. When the sun goes down, the temperature can drop 60 degrees Celsius within an hour. The rocks release their stored heat quickly into the thin air. By midnight, the temperature at Jezero will be around negative 80 degrees Celsius. The rover is designed for this. Its electronics are housed in a warm electronics box, maintained at roughly negative 40 degrees Celsius, or warmer, through the use of internal heaters powered by the radioisotope system. Without this thermal protection, the electronics would fail within hours of the first Martian night. Perseverance has survived over 1,400 Martian nights. The dust devil to the east has long since dissolved, its dust dispersed into the general haze. The crater floor is settling into the last of the afternoon light. Somewhere to the south, beyond the crater's inner rim, the plains of Isidis Planitia extend northward for hundreds of kilometers, a vast, ancient impact basin that was itself once filled with water, now flattened and quiet, one of the lowest points on the northern hemisphere of Mars. And somewhere beyond that, if you could travel roughly 3,000 kilometers to the southwest, you would reach the edge of something that has no equivalent anywhere on Earth. The ground begins to drop away. Not gradually, not like a hillside or a valley. It drops away all at once in a cliff face that in some places is more than 7 kilometers high, and it keeps dropping into a canyon system so large that geologists struggled for years to find an analogy for it on any other world. You move toward the edge of Jezero's western rim, and below you the plains tilt very slightly, barely perceptibly toward the west, toward the ancient volcanic highlands, toward the place where the crust of Mars was once pulled apart, along a zone of stress that stretched for a quarter of the planet's circumference. The sediment beneath your feet thins as you move. The layered delta rock gives way to older, less sorted material, breccia from the original impact that formed the crater, coarse and angular, not smoothed by water but shattered by violence, and then left alone for nearly 4 billion years. The western rim of Jezero rises perhaps 400 meters above the floor. Standing at its crest, looking west, the plain beyond the crater extends in every direction with the flatness that only comes from enormous age. The surface here was shaped by lava flows, so old they have been eroded and filled and re-eroded until the original volcanic textures are barely visible. Craters of every size dot the surface, small fresh craters bright with ejected material, old craters worn almost flat, ghost craters so ancient you can only see them from orbit as subtle circular patterns in the rock. Each crater is a timestamp. The density of craters on any given Martian surface tells geologists roughly how old it is. The terrain to the west is very old. The haze in the air is thicker in the distance. Suspended dust reduces visibility on Mars to typically a few tens of kilometers, far less than the thousands of kilometers of visibility possible on a clear Earth day. But even through the haze, the terrain ahead has a quality of immensity, a flatness that is not emptiness but age, the flatness of a world that has been sitting here longer than the continents of Earth have been in their current positions, longer than complex animal life has existed, longer than the oceans of Earth have been salty. You begin to move west, away from Jezero, away from the delta and the waiting sample tubes and the quiet rover. The plain stretches before you. The dust crunches softly beneath each step, or would if the sound carried properly in this air. The wind at your back is gentle, no more than 5 meters per second, carrying fine particles that swirl at ankle height before settling again. In the far west, barely distinguishable through the haze, there is something unusual about the horizon. The ground does not simply flatten out toward it. There is a quality of depth to the western distance that is different from the eastern horizon. It is not a mountain range, it is not a ridge, it is an absence, a place where the ground is not. The plains of Lunae Planum are ending, and beyond them, the land falls away into one of the longest, deepest, widest chasms in the solar system. You are walking toward Valles Marineris. The haze around you is thickening slightly as the afternoon progresses, and the sky above has taken on the deeper, dustier orange of a Mars afternoon past its peak brightness. Each step covers ground that no human foot has ever touched, that no living thing, as far as anyone knows, has touched in billions of years. The dust is the same dust that covered this plain when the first single-celled organisms were beginning to divide in Earth's young oceans. The rocks are older than the Cambrian, older than the first animals. The stillness here is not the stillness of a quiet room or a silent forest. It is the stillness of geological time, of a world that processes its changes over millions of years, not days. And the ground is still dropping away, very slowly westward. The gradient is so gentle, you would barely notice it without instruments. Perhaps 1 degree of slope over the final 100 kilometers before the edge. The ancient volcanic plains here tilt almost imperceptibly toward the Great Canyon. Erosion has been minimal. There is no rainfall on Mars, no rivers running today, only the wind and the seasonal cycling of carbon dioxide frost at the poles. The surface preserves every feature for extraordinary lengths of time. Footprints left here would likely remain for millions of years before wind erosion smoothed them away. You keep walking. The haze deepens. The temperature continues its afternoon decline. Mars is turning, and the sun is no longer at its highest, somewhere 200 kilometers to your northwest. Perseverance is still moving, its cameras still recording, its instruments still sampling the air, its wheels still pressing their distinctive tread pattern into the ancient delta dust. Its signal is traveling upward to one of the relay orbiters, above and then onward, across 170 million kilometers of space toward Earth, where scientists in Pasadena are reading its data at a desk with a cup of coffee in a building with windows under a sky that is a proper blue. You are not there. You are here. And the edge is very close now. The ground ahead of you is changing. The ancient basalt plain is giving way to fractured terrain, zones where the crust has been stressed and cracked and pulled apart. The cracks run roughly east to west, parallel to each other, some of them meters wide, some of them hundreds of meters. This is the transition zone. This is where the structural integrity of the Martian crust began to fail under the stress of the Great Rift system that runs to the west, the system that eventually opened into something so large it does not have a single agreed comparison anywhere in the solar system. You stop at the edge of the first large fracture. It is perhaps 20 meters wide, and the walls drop straight down into shadow. Far below, the floor is covered in fallen material, boulders and slabs that have dropped from the walls over billions of years. The fracture extends east and west as far as you can see through the haze, running parallel to a dozen others behind you and a dozen more ahead. This is where Valles Marineris begins. Not with drama, not with a single cliff, but with fractures, with the slow pulling apart of a world's crust, with cracks that grew over hundreds of millions of years as the volcanic weight of the Tharsis Bulge to the west deformed the entire Martian crust and stretched it along this line until it broke. The fractures multiply as you move west. They deepen, they widen. The flat plain between them narrows and then disappears, and the fractures merge, and the ground drops away, and the canyon opens before you. You pause here, at the edge of the fracture zone, and look back east, the direction you came from, the direction of Jezero. The crater is invisible from here, too far and too small against the scale of the plain, but you know it is there, 45 kilometers wide, its delta preserved in sedimentary layers, its sample tubes waiting in the dust. The distance between here and there, a few hundred kilometers of flat, cold, ancient basalt, is nothing by Martian standards. The planet is roughly half the diameter of Earth, with a surface area nearly equal to all the dry land on Earth. This plain stretches for thousands of kilometers in every direction. You have barely moved. A thought settles into you with the weight of the numbers. Mars has a surface area of approximately 144.8 million square kilometers. Of that entire surface, human technology has physically touched fewer than 30 square kilometers in total. All the landing sites combined, all the rovers, all the landers, all the impactors, all the probes, since Mariner 4 flew by in 1965. 30 square kilometers on a world with the same land area as Earth. The exploration has barely begun. The wind shifts slightly, coming now from the southwest, from the direction of the volcanic highlands. You can feel it, or you would feel it, as a slight pressure against your suit, barely perceptible but constant. The southwest winds on Mars are not unusual. The planet's atmospheric circulation is driven by the same principles as Earth's, differential heating between equator and poles, the Coriolis effect from the planet's rotation, the influence of topography, but without oceans to moderate temperature gradients, and without the complex moisture dynamics that shape Earth's weather. Martian weather is simpler in some ways and more extreme in others. Regional dust storms can develop within days and spread across hemispheres within weeks. The global storm of 2018 grew from a regional disturbance in the Hellas Basin, a huge impact crater in the southern hemisphere, and within weeks had grown to cover an area larger than North America, and within months had encircled the planet completely. When the global storm reached maximum opacity, the dust in the atmosphere reduced the amount of sunlight reaching the surface to roughly 1% of normal. It was not dark in the way night is dark. It was more like being inside a very thick orange fog, where the light had no direction, just a diffuse glow coming from nowhere in particular. Surface temperatures dropped because the dust was absorbing the solar energy that would normally have reached the ground. The atmosphere itself warmed. The temperature gradient between the warm dust-laden atmosphere and the cold surface became inverted in some locations, suppressing the convective mixing that normally helps carry heat vertically. For opportunity, NASA's rover that had been operating on the far side of the planet since 2004, the storm meant the end. Opportunity was solar-powered. It needed sunlight to charge its batteries. When the dust reduced sunlight to 1%, the rover's batteries could no longer sustain the heating systems required to keep its electronics alive during the Martian night. Its last communication was received on June 10, 2018. Engineers spent 8 months attempting to re-establish contact, sending over 1,000 recovery commands. The final command was sent on February 12, 2019. No response came. Opportunity had been active for 5,111 sols, nearly 15 Earth years, and had traveled 45.16 kilometers across the Martian surface, far beyond its original design life of 90 sols and 1 kilometer. 15 years of movement, then one storm. The plane around you carries no memory of that storm. The dust it deposited has mostly been redistributed by subsequent winds, layers added to layers, the record of any individual storm blending into the general accumulation of centuries. Stratigraphy on Mars is more complex than it appears from the surface. Even in the wind-blown plains, there is structure, fine laminations of dark and light material, layers rich in iron minerals, alternating with layers rich in silicate dust, the record of changing seasons and shifting atmospheric chemistry laid down one thin film at a time. The regolith, the layer of broken rock and dust that covers most of Mars's surface, is not deep everywhere. In some locations, it is only a few centimeters thick, sitting atop intact bedrock. In others, particularly in ancient impact basins and low-lying plains, it reaches depths of tens of meters. The regolith is not simply ground-up rock. It has been chemically altered by billions of years of interaction with the thin atmosphere, with ultraviolet radiation that reaches the surface directly, without the filtering that Earth's ozone layer provides, and with trace amounts of water vapor that occasionally condenses onto mineral surfaces and drives slow chemical reactions. The result is a surface layer that is chemically reactive in ways that create challenges for potential biology and for human explorers who would need to manage the reactivity of Martian dust as a health hazard. Perchlorate, for instance. Martian soil contains perchlorate salts at concentrations between 0.4 and 0.6% by mass, levels that would be considered highly contaminated by Earth environmental standards. Perchlorates are oxidizing agents, and on Mars they appear to have formed through atmospheric chemistry driven by ultraviolet radiation acting on chlorine-bearing compounds. They are found globally in the Martian soil, not just in specific locations. For human explorers who might accidentally ingest dust, a real risk in any environment where fine particles adhere to suits and equipment, the perchlorate concentration represents a genuine physiological concern, since perchlorates disrupt thyroid function. Future human missions to Mars will need dust control and decontamination protocols that go well beyond anything required in current spaceflight. The chemistry of this dust has been shaped by billions of years of ultraviolet bombardment and atmospheric chemistry, producing a surface that is simultaneously ancient and chemically active, a world that looks dead and inert, but is, at the molecular level, still reacting, still changing, still driven by the slow redox chemistry of iron and oxygen and sulfur and chlorine in a thin, cold, irradiated atmosphere. You look down at the dust near your feet and see it differently now. Not just color, not just texture, a 4 billion year chemical experiment still running. The fracture you are standing beside goes down into shadow. The sunlight reaches only the upper portions of the walls, and the lower sections disappear into a dimness that is not quite darkness, but is too deep for the low-angle afternoon sun to penetrate fully. The walls are layered, visibly layered, the way sedimentary rock is layered on Earth, but older. Some of the layers in the fracture walls are volcanic, laid down during periods of ancient lava flooding. Some are sedimentary, deposited when water was present. Some are a mixture, reworked by both processes. On the lower walls of some of the deeper fractures in the Valles Marineris system, which you are approaching, geologists have identified something called recurring slopelania, dark streaks that appear on steep slopes during the warm Martian season and fade during the cold. For years, these were considered possible indicators of liquid water flowing just below the surface, creating wet soil that darkened the slope and slid slowly downhill. More recent analysis has suggested an alternative explanation: granular flows of dry material triggered by the thermal expansion of carbon dioxide frost, or by the deliquescence of perchlorates, the absorption of water vapor from the atmosphere by salt minerals, which can lower the freezing point of water enough to create brief episodes of extremely salty liquid. Whether any liquid water is involved even transiently remains an open and contested question in Mars science. The recurring slopelenia have been identified in the walls of Valles Marineris itself, on steep slopes where the sun reaches the rock surface in the afternoon and warms it above a critical threshold. You will see them for yourself. The ground ahead is increasingly fractured. The cracks have grown wider, and the walls between them have eroded down, filling the fractures with rubble. The terrain is rougher now, less like an ancient plain, and more like a place under stress, a place where geological forces are still legible in the broken landscape. The transition from Lunae Planum to the edge of Valles Marineris takes several tens of kilometers, not a single cliff at a single line, but a gradual dissolution of the flat highland surface into increasingly broken terrain until the flat surface simply no longer exists, and the canyon opens below in a scale that refuses to be held in a single thought. The haze around you has thinned slightly in the late afternoon. The wind has dropped to nearly nothing. The dust at your feet is barely moving. The light is long and orange, and coming from a sun that is now perhaps 20 degrees above the western horizon. And in the middle distance, between you and the setting sun, there is no more ground. The canyon begins. Not gradually anymore, suddenly. The fractures behind you have prepared you, but they have not prepared you for the moment when you step to the rim of the main trough and look north and look south and look down and understand, with the part of your mind that processes real scale rather than abstract numbers, what 4,000 kilometers of open rock actually means. The northern wall of the main Valles Marineris trough drops away below your feet. The first 100 meters is nearly vertical, clean, dark basaltic rock, faintly layered, catching the last of the afternoon light on its upper face. Below that, the wall recedes slightly as it descends, step by step, layer by layer, each ledge the trace of a different geological period. The wall is 6 kilometers deep here. The floor is invisible in shadow, but you know it is there, relatively flat, covered in ancient landslide debris and wind-blown sediment, a floor that in some parts of the canyon is 200 kilometers wide. You are standing at the edge of the largest canyon in the solar system, and there is still light. And the air is moving gently around you, carrying its dust, its perchlorates, its iron oxide, its ancient chemistry, across the edge and down into the dark. The canyon wall drops away from your feet in layers. Not a single sheer face, not the clean vertical drop of a cliff cut by a river. The walls of Valles Marineris are a geological record, stacked in horizontal bands, each one representing a chapter in the history of a planet. Lava flows, impact ejecta, wind-deposited sediment, ancient lakebeds, volcanic ash, compressed together over 4 billion years, and then exposed all at once when the crust pulled apart and the ground fell away. You are reading that record from the top down, and it goes deep. It goes so deep that the lowest layers, visible only from the canyon floor far below, are among the oldest exposed rock anywhere on Mars. The eastern Valles Marineris, the section called Coprati Chasma, is where the walls are tallest. Here the rim sits more than 7 kilometers above the canyon floor. For comparison, the deepest point of Earth's Mariana Trench is just under 11 kilometers below sea level. The difference is that the Mariana Trench is measured from the ocean surface to its floor, from water to more water. Valles Marineris is open. You are standing in open air above a rock floor 7 kilometers down. The scale is not hidden by water. It is simply there, exposed, unambiguous, waiting for the mind to process it. The mind resists. You look north along the rim. The canyon wall curves very slightly with the curvature of the planet and extends to the horizon. You look south, the same. The canyon runs roughly east to west, 4,000 kilometers in total length, and from any single point on the rim, you can see perhaps 50 or 60 kilometers of it through the Martian haze before it fades into the suspended dust. The full length is not visible from any surface vantage point. It is only from orbit that the entire system can be seen at once, a dark gash across the equatorial region of Mars, visible even from the distance of Earth through a good telescope on a night of clear seeing. The canyon is not a single feature, it is a system. Valles Marineris is the collective name for a series of interconnected chasmata, deep troughs that formed through a combination of tectonic extension and collapse. The dominant mechanism was not erosion by water or wind, as the Grand Canyon was carved. It was the stretching and cracking of the Martian crust under the enormous gravitational stress imposed by the Tharsis Bulge, a vast volcanic dome roughly 5,000 kilometers across and 10 kilometers high, located just to the west of the canyon system. Tharsis represents the largest concentration of volcanic material in the solar system. Its mass has actually deformed the rotation of Mars slightly. The planet bulges measurably in the direction of Tharsis, and the excess mass has caused Mars's rotational axis to shift over geological time. The weight of that volcanic accumulation stretched the crust to the east, creating the system of fractures that eventually collapsed to form Valles Marineris. The canyon, in other words, is a scar left by volcanoes that are not even here. It is the consequence of events that happened hundreds of kilometers to the west, expressed as an absence, as rock that fell away and left this chasm behind. Built by what is not here, defined by what is missing. You step back slightly from the rim. The edge is not safe in any conventional sense. The rim rock is fractured and unstable in places, undercut by millions of years of mass wasting, by the gradual collapse of wall material into the canyon below. Mars has no erosion by rainfall, no freeze-thaw cycles driven by liquid water, but it has gravity and it has temperature swings. The surface temperature here cycles between roughly -80 degrees Celsius at night and perhaps 0 degrees Celsius in the afternoon on a summer day near the equator. That daily swing of 80 degrees causes thermal expansion and contraction in the rock, and over millions of years it fractures the rim material and sends it slowly in pieces down the canyon walls. The landslide deposits on the canyon floor are enormous. Some of them extend 20 to 30 kilometers from the base of the wall, spread across the canyon floor in lobes of jumbled rock that geologists call stirrstroms, long run-out landslides that travel far further than their height would predict on Earth. On Mars, the low gravity, 38% of Earth's, allows landslide debris to travel farther before stopping. Some of the largest Martian landslides may have been triggered by Marsquakes, seismic events detected by NASA's InSight lander between 2018 and 2022. InSight recorded hundreds of Marsquakes during its operation, the largest of which reached a magnitude of approximately 5 on the Richter scale, modest by Earth standards, but significant on a planet with a colder, more rigid crust that transmits seismic energy more efficiently than Earth's warmer, more plastic mantle. InSight is no longer operating. Its solar panels accumulated enough dust over 4 years of operation that they could no longer generate sufficient power to keep the lander warm through the Martian winter. On December 21st, 2022, NASA declared the mission complete. InSight remains on the Martian plain of Elysium Planitia, a few thousand kilometers northeast of where you are standing, its instruments silent, its solar panels coated in the same fine iron oxide dust that coats everything here eventually. The seismic data InSight gathered before it fell silent revealed something unexpected about Mars's interior. The planet has a liquid outer core of iron, sulfur, and possibly oxygen, approximately 1,800 kilometers in radius. Surrounding it is a rocky mantle, and above that the crust, which InSight found to be between 24 and 72 kilometers thick, depending on location, thicker in the ancient southern highlands and thinner in the younger northern lowlands. The crust beneath you, at the edge of Valles Marineris, is in a transition zone. The canyon itself may have formed partly because the crust here was already thinner, already under greater stress from the Tharsis loading, already closer to the structural threshold at which it could no longer hold together under its own weight. You look down again into the canyon. The shadow in the depths is complete now. The sun has moved low enough that direct light no longer reaches the canyon floor anywhere along this section, but the upper walls still catch the orange light, and the layered rock glows in shades of rust and tan and pale gray. You can count the layers from here. Not individually, there are too many, but in broad units. A thick dark band near the base of the lit section is basalt, volcanic in origin, perhaps 3 billion years old. Above it, a paler unit with finer texture is sedimentary, material deposited by wind or water long after the basalt cooled. Above that, another dark volcanic layer, evidence of a later eruption. The stratigraphy here records not one era of Mars's history, but several, each episode of geological activity, leaving its mark in a layer that was then buried and preserved until the canyon opened and exposed it to the sky again. The light on the upper walls is fading. Martian twilight lasts longer than Earth's twilight because the suspended dust in the atmosphere scatters light at low sun angles more efficiently than the clear air of Earth. After the sun drops below the horizon, scattered light from the dust high in the atmosphere continues to illuminate the surface for 30 to 40 minutes. During this time, the sky transitions from orange to deep red to a murky purple, and then the stars appear, not gradually the way they appear through Earth's thick atmosphere, but quickly because there is so little atmosphere here to hold the sky's brightness after the sun is gone. The stars over Valles Marineris are extraordinary. The Martian atmosphere carries almost nothing to dilute them. No moisture, no city glow, no thick blanket of nitrogen to soften their edges. The stars are points. The Milky Way is a band of individually distinct lights rather than a smear, and above the eastern wall of the canyon, moving slowly against that background, is a blue-white point brighter than anything else in the sky. Earth. The light reaching your eyes left that small blue point approximately 9 minutes ago. The people on it do not know you are looking at them. Below you, in the absolute shadow of the canyon floor, there is no light at all. The temperature at the rim has dropped 20 degrees in the last hour. The rocks around you are releasing their stored heat into the thin atmosphere, and the air close to the ground is cooling faster than the air above it, creating a temperature inversion, a layer of cold air trapped near the surface by warmer air above. This happens every night on Mars. It suppresses convection, preventing the vertical mixing that would otherwise moderate the surface temperature drop. By midnight, the rim of Valles Marineris will be near -70 degrees Celsius. In the canyon below, the temperature drop will be less severe. The walls retain heat longer than the open plain, and the enclosed geometry of the canyon creates its own microclimate. The canyon has air that is slightly denser at its floor than at its rim. The difference is small. The floor pressure might be 10 to 15% higher than the rim pressure, but in an atmosphere as thin as Mars's, even a small increase in density is meaningful. It means the canyon floor is marginally more hospitable to potential liquid water, marginally more shielded from ultraviolet radiation by the additional column of air above. If liquid water ever exists transiently on present-day Mars, the canyon floor is one of the more likely places. The recurring slope lineae you read about earlier, those dark streaks on steep slopes, have been detected here on the inner walls of Valles Marineris, in the sections where afternoon sunlight heats the rock above a thermal threshold. You cannot see them in the current shadow, but they are there on south-facing slopes where the sun reaches longest, faint dark lines running downslope for tens to hundreds of meters, appearing in the warm season and fading when temperatures drop. You stay at the rim for a long time. The canyon below is filled with a darkness so complete it has texture. The walls recede into it. The floor is swallowed by it. The only light is from above. The stars, the distant blue point of Earth, the thin band of the Milky Way crossing the sky from east to west. The canyon simply goes down, and the darkness at the bottom is the darkness of a place that has not seen direct sunlight for billions of years in its deepest sections, a darkness built from the same geological processes that built the mountain you will visit next. Because to the west of where you stand, 2,000 kilometers across the volcanic plains of Tharsis, something has been waiting. Something that rises nearly 3 times higher than the rim you are standing on now. You turn away from the canyon. You turn west. The plains of Tharsis extend before you in the Martian night, their surface faintly visible under starlight, rolling almost imperceptibly upward. The gradient is so shallow, it is invisible to any human sense of slope. You would walk for hours, for days, before an inclinometer would register a consistent rise. But the rise is there. The entire Tharsis region is a crustal bulge, roughly 10 kilometers higher than the mean Martian elevation, and it dominates the western hemisphere of the planet. 3 massive shield volcanoes sit along its crest: Olympus Mons, Valles Mons, and Jezero Mons, each one enormous by Earth standards, each one dwarfed by what sits at the northwestern edge of the plateau. Olympus Mons, the largest volcano in the solar system, possibly the largest mountain of any kind anywhere in the solar system, depending on how you measure. It covers an area of approximately 300,000 square kilometers, roughly the size of the state of Arizona, or the entire country of Italy. Its base diameter is 600 kilometers. It rises 21.9 kilometers above the mean Martian surface level. Its summit caldera, the collapsed depression at its peak left by the draining of magma chambers below, is 80 kilometers across and 3 kilometers deep. You walk toward it through the Martian night. The stars turn slowly overhead as Mars rotates. The planet completes one rotation in 24 hours and 37 minutes, and the stars trace arcs across the sky, just as they do from Earth. But the Martian sky is darker, the stars are harder, and the absence of any moon as large as Earth's moon means the night surface is lit only by Phobos and Deimos, the 2 small moons of Mars, and by the stars themselves. Phobos rises in the west and sets in the east. It orbits Mars so quickly, completing one full orbit in just 7 hours and 39 minutes, faster than Mars rotates, that it moves visibly across the sky over the course of a single night, rising and setting twice between dusk and dawn. It is not bright. Phobos is only 22 kilometers in its longest dimension, an irregular, heavily cratered object that was almost certainly a captured asteroid rather than a body that formed alongside Mars. Its surface is covered in a layer of fine regolith, several meters deep, the accumulated debris of billions of years of micrometeorite impacts. It is so close to Mars, only 6,000 kilometers above the surface, compared to the Moon's 384,000 kilometers from Earth, that from the Martian surface it appears roughly 1/3 the angular diameter of Earth's moon. Deimos is smaller still, 12 kilometers across, and orbits farther out, taking 30 hours to complete one orbit. From the surface, it appears as a bright star that moves slowly across the sky over 2 nights, barely distinguishable from the background stars, except by its movement. The 2 moons are doomed. Phobos is slowly spiraling inward, drawn toward Mars by tidal forces. In approximately 30 to 50 million years, it will either collide with the Martian surface or be torn apart by tidal forces before it can impact, creating a ring of debris around Mars, the first ring the planet has ever had. Deimos, orbiting farther out, is slowly spiraling away as Earth's moon is slowly moving away from Earth. In the very long run, Mars will lose both its moons, but not tonight. Tonight, Phobos crosses the sky in a bright arc, and the plains of Tharsis are lit by its faint reflected sunlight, and the volcanic surface is the color of old rust under the cold stars. A moon that will not last. Moving toward its end, one orbit at a time. The ground beneath your feet has changed. The sedimentary and fractured terrain near Valles Marineris has given way to volcanic plains, broad, flat lava flows that spread outward from the Tharsis volcanic centers hundreds of millions to billions of years ago. The surface here is among the youngest on Mars in places. Some Tharsis lava flows have been dated to less than 100 million years ago, which is geologically recent on a planet 4.5 billion years old. A few studies have suggested volcanic activity on Mars may have occurred as recently as a few million years ago, based on the pristine appearance of certain lava flows visible from orbit. Mars may not be entirely dead. The lava flows beneath your feet have a texture that is different from the ancient cratered highlands to the east. They are smoother, more uniform, with fewer impact craters because they are younger and have had less time to accumulate the scars of incoming debris. In some places, the surface is ropey and folded, a texture called pahuhu, the same word used for the same texture in Hawaiian lava flows on Earth, formed when the outer crust of a lava flow cools and solidifies while molten rock continues to flow beneath it, wrinkling the surface like skin on cooling custard. In other places, the surface is broken and jagged, a texture called a'a, formed when the lava flow moves quickly enough to fracture its own cooling crust. You are walking across frozen waves of ancient fire. The stars are still bright. Earth has moved slightly higher above the eastern horizon. The temperature at the surface is -65 degrees Celsius and falling, but the volcanic rock beneath your feet absorbed heat during the day and is releasing it slowly, and the ground here is a degree or two warmer than the open plains to the east. The difference is imperceptible to any human sense, but it is real and it is measured. Ahead, in the starlight, the horizon has changed. The Tharsis Plains were already elevated, 10 kilometers above the mean Martian datum, the reference level equivalent to sea level on a planet with no sea. You have been climbing without feeling it, the gradient so shallow that it has registered only as a slightly longer walk, a slightly greater distance to each new feature on the horizon. But the horizon ahead is wrong now. It does not curve away cleanly the way a planetary horizon should. It rises. The sky above the western horizon is occluded. The stars that should be there are not there, because something is blocking them. The escarpment of Olympus Mons. Before the mountain itself begins its gentle slope, there is a cliff, a circular cliff, the escarpment that rings the base of the volcano, that in some places rises 8 kilometers in a single vertical face. This is not the mountain, this is the border of the mountain. The escarpment marks the boundary between the surrounding volcanic plains and the base of the shield, a boundary created over billions of years as the volcano grew taller and its edges spread outward and eventually overran the surrounding terrain, creating an overhang in some sections where the lava flows at the base extend beyond the material above them. 8 kilometers of vertical cliff. The tallest sea cliffs on Earth, those of the Kalapapa Peninsula on Molokai in Hawaii, reach just over 1 kilometer in height. The sea cliffs of the Coromandel Peninsula in New Zealand are a few hundred meters. The escarpment of Olympus Mons is 8 times the height of anything comparable on Earth, and it runs continuously for hundreds of kilometers around the base of the volcano. You stand at the base of the escarpment and look up. The cliff face above you catches the very first light of the Martian dawn, a faint brightening of the eastern sky that sends a diffuse orange glow across the plain behind you and touches the upper sections of the escarpment wall with the palest possible light. The lower sections are still in complete shadow. The wall is layered, basaltic lava flows stacked on top of each other, each flow between a few meters and several tens of meters thick, the accumulated record of eruptions spanning hundreds of millions of years. The total thickness of volcanic material on Olympus Mons, measured from its base to its summit, is a geological accumulation unlike anything on Earth. On Earth, the reason no volcano grows this large is plate tectonics. Earth's crust is divided into tectonic plates that move continuously, driven by convection in the mantle below. When a mantle plume, a column of unusually hot rock rising from deep in the mantle, reaches the surface, it creates a hot spot that generates volcanic activity. But because the plate is moving over the hot spot, the volcanism does not stay in one place. The Hawaiian Islands are the most visible example. The same mantle plume created every island in the chain, but the Pacific plate has been moving northwestward over it for millions of years, so each island formed over the hotspot and then moved away as a new one began to form. The result is a chain of islands rather than a single enormous volcano. Mars has no plate tectonics. The crust does not move. The mantle plume that fed Olympus Mons sat beneath the same point on the Martian surface for billions of years, pumping lava upward through the same conduit system, building the same volcanic structure, taller and wider, century by century, eruption by eruption. There was no plate to carry the material away. It simply accumulated for perhaps 2 billion years. The result is standing above you. You begin to move upward. There is a path here, not a path made by any person or any machine, but a natural ramp where the escarpment wall has partially collapsed, where ancient landslides have piled debris against the cliff face and created a slope shallow enough to climb. The material underfoot is broken basalt, angular fragments ranging in size from gravel to boulders the size of houses, covered in the ubiquitous reddish dust. The climb is steep by Martian standards, but would be manageable in the reduced gravity, 0.378 of Earth's, which means your effective weight here is less than 40% of what it would be at home. The escarpment rises around you. You are climbing through the geological history of the volcano. Older flows at the bottom, younger flows above, the stratigraphy inverted from what you read in Valles Marineris. Here the oldest rock is deepest, and the youngest is at the top, because each new eruption deposited material over what came before. Every layer above you is younger than the one you are standing on. The dawn is progressing. The eastern sky behind you is brightening quickly. Mars has a thinner atmosphere to hold the pre-dawn glow, and the transition from night to day is faster here than on Earth. Within 30 minutes of the first brightening, The sun will clear the eastern horizon, and the surface temperature will begin its daily climb from its overnight low. You reach the top of the escarpment as the sun rises. The view behind you, east across the Tharsis Plains, toward Valles Marineris, toward Jezero, toward the sample tubes waiting in the dust of an ancient lake, is extraordinary. The plain extends to the horizon in every direction, and the horizon is far away because you are high, and in the rising light the surface is a complex tapestry of volcanic textures and ancient impact scars and wind-sculpted ridges, all rendered in the low, long light of early morning that brings out every surface feature in sharp relief. You turn west, you look up at the slope of Olympus Mons, and the mountain does not look like a mountain. This is the thing about Olympus Mons that no description fully prepares you for. The average slope of its flanks is less than 5 degrees. In some sections, it is closer to 2 or 3 degrees. If you were placed at any point on the volcano's flank with no knowledge of where you were, you would see a gently inclined plane extending in all directions. You would feel a very slight uphill tilt. You would not feel that you were on a mountain at all. The volcano is so wide, 600 kilometers across, that its curvature is comparable to the curvature of the planet itself. The summit is not visible from the base, not because of clouds or haze, though haze plays a role, but because the mountain curves away with the planet before the geometry allows a line of sight to the top. To see Olympus Mons as a mountain, you have to leave Mars entirely. From orbit, the shape is clear, a vast circular dome rising smoothly from the surrounding plains, the summit caldera visible as a complex depression at its center, the escarpment visible as a sharp circular edge where the dome meets the plain. The volcano is so tall that it extends above most of the Martian atmosphere. The summit is above 99% of the planet's atmospheric mass. At the summit, the atmospheric pressure is approximately 30 pascals, less than 1/20th of the already thin pressure at the base. The air at the top of Olympus Mons is so thin that it is, for most practical purposes, outer space. You begin the long walk upward. The surface here is different from the fractured terrain near Valles Marineris. The lava flows on the flanks of Olympus Mons are younger, some of them perhaps 100 million years old, geologically fresh by Martian standards, and they have had less time to be broken down by impact and thermal cycling. The surface is smoother, the rocks less angular, the dust thinner in places where the gentle volcanic slope allows wind to carry it away before it accumulates deeply. The dark gray of unweathered basalt shows through in patches, almost black in the morning light, making the surface look mottled. Dark gray and rust red and irregular patches that extend for hundreds of meters in every direction. The impact crater density here is low. Scientists use crater density to estimate surface age. The more craters, the older the surface, because older surfaces have had more time to be struck by incoming debris. The flanks of Olympus Mons have far fewer craters than the ancient highlands to the east. This confirms what the rock composition suggests. The volcano is geologically young. It has not had time to accumulate the dense cratering record of the old terrain around Jezero Crater. The sun is fully up now. The sky has its familiar daytime color, a pale, dusty orange. The iron oxide haze catching the morning light and scattering it across the entire sky dome. The sun is to the east, behind you as you climb west, and your shadow extends long in front of you up the gentle slope. The temperature at the surface is rising. the rock warming under the direct solar irradiance of about 590 watts per square meter, less than half the 1,360 watts per square meter that Earth receives, but enough to warm the dark basalt significantly above the ambient air temperature. You walk. The distance to the summit from any point on the escarpment is enormous, 300 kilometers of horizontal distance, rising just over 21 kilometers in altitude. At a walking pace of 4 kilometers per hour, the summit is 75 hours away. You are not walking at a human pace here, or rather you are walking, but the science of this place compresses time and distance in the way that stories do, so the details of the climb unfold not hour by hour, but as a continuous reading of the volcanic record beneath your feet. Every step is a different era. Every layer is a different Mars. At 50 kilometers from the escarpment, the surface changes. You cross a boundary into a zone of more recent lava flows that in some areas retain the smooth, glassy texture of freshly cooled basalt, barely touched by the billions of years of weathering that have aged the terrain at lower elevations. These flows are so well preserved that orbital images of them were initially mistaken for evidence of recent geological activity. Further study confirmed their age at perhaps 50 to 100 million years, ancient by human timescales, but young in geological terms, young enough that the volcanic conduits that fed them may still exist below the surface, filled with cold, solid basalt, waiting for a future heat source that may never come, or may come sooner than anyone expects. The interior of Mars is cooling. The planet is smaller than Earth, and smaller bodies cool faster. They have less volume relative to their surface area, and heat escapes more efficiently. Mars lost most of its internal heat-driven geological activity billions of years ago, which is why it has no active plate tectonics and why its magnetic field collapsed. But cooling does not mean dead. The mantle of Mars is still warm enough to be partially molten in places. Some models of Martian interior temperature suggest that magma could still be generated in the mantle beneath the Tharsis region under the right conditions. Whether those conditions exist today or will exist again in the future is unknown. The mountain you are climbing may not be finished. At 100 kilometers from the escarpment, you stop and look around. The plain below the escarpment is no longer visible. It has been lost not in distance, but in the gentle curvature of the volcano itself. The slope has carried you high enough that the terrain below the escarpment has curved below your horizon. In every direction, the surface is the same, a gently inclined, slightly textured volcanic plain, dark and quiet under the morning sun. There is no drama here in the conventional sense, no sharp ridge, no rocky spire, no precipice, just this enormous, silent, ancient slope extending to every horizon, curving gently upward toward a summit that is still 200 kilometers away. The silence on Olympus Mons is different from the silence in Jezero Crater or at the rim of Valles Marineris. At Jezero, the silence had the quality of a lakebed, a place that was once full and is now empty, where the absence of water is the most present thing. At Valles Marineris, the silence had the quality of depth, of a space so large it swallows sound as completely as it swallows light. Here, on the flank of Olympus Mons, the silence has the quality of height, of altitude, of a place so elevated above everything else that the connections to the lower world have been thinned to almost nothing. The atmosphere here is thinner than at the crater rim. The wind, when it moves, is barely perceptible. The dust is thinner. The temperature swings are smaller because there is less atmosphere to lose heat into at night. The mountain absorbs everything and gives back nothing. Somewhere beneath your feet, the conduit system that fed the eruptions that built this structure extends downward through the crust and into the upper mantle, a network of tubes and chambers and fractures through which, for billions of years, molten rock moved upward from the deep interior of the planet and spread across the surface in flows that added, meter by meter, to the structure you are standing on. Those conduits are cold now, filled with solidified basalt, but they are there, running downward through 21 kilometers of volcanic rock, a plumbing system for a machine that has been idle for millions of years. You continue upward. 200 kilometers from the escarpment, the slope has carried you above the main dust haze layer. The sky above you is darker, not the deep black of space, but a deeper, richer color than the dusty orange of lower elevations. The sun is brighter here, less filtered by the atmospheric dust that diffuses it at lower altitudes. The horizon is slightly closer because you are on a curved surface, and the curvature of the planet is more apparent from this height. On a clear day at this elevation, the escarpment, 8 kilometers of vertical cliff, would be visible to the south and east, a dark line drawn across the pale plain far below. The temperature here at the summit elevation is lower than at the base, not dramatically lower because the thin atmosphere does not carry heat efficiently in either direction, but lower. The average temperature near the Olympus Mons summit is in the range of -100 degrees Celsius at night, warming to perhaps -50 or -60 during the day. The temperature swing from day to night is smaller here than at lower elevations because there is so little atmosphere to drive convective heat transfer. The caldera appears ahead, not as a dramatic drop into the earth, as a gradual transition. The slope you have been climbing for the entire ascent simply levels off and then, over a distance of a few kilometers, begins to descend. The rim of the caldera is not a sharp edge. It is a rolling, fractured zone where the surface has subsided as the magma chambers beneath it drained and the roof rock collapsed. The caldera is roughly 80 kilometers across. You cannot see the far wall clearly through the thin haze, but you can see it, a dark line on the far horizon that is the caldera's opposite rim. Beneath your feet, the caldera floor is 3 kilometers below the rim level. The inner walls are steep, much steeper than the outer flanks of the volcano, and layered with the same basaltic stratigraphy visible everywhere on this mountain. The floor is relatively flat, covered in a thin veneer of dust and the remains of the last flows to fill the caldera before the volcano went quiet. There are smaller craters within the caldera, secondary calderas, nested depressions formed by separate collapse events, each one representing a different episode of magma withdrawal and surface subsidence. The caldera is not silent in the way the flanks are silent. Something about being enclosed, even in an enclosure 80 kilometers wide, even on a world with almost no atmosphere, changes the quality of the space. The caldera walls rise around you on 3 sides, blocking the distant horizon, reducing the sky overhead to a slightly smaller dome. The wind inside the caldera behaves differently than on the open flanks. It circulates, caught by the geometry of the enclosed space, creating subtle eddies of dust along the inner walls. The morning sun lights the eastern inner wall in brilliant detail, while the western wall remains in shadow. The contrast between the lit and unlit sections of the caldera interior is sharp because the thin atmosphere carries almost no scattered light into the shadows. You stand at the caldera rim, 21.9 kilometers above the surrounding plains, above 99% of the Martian atmosphere. Below you, the caldera floor is darker than the outer surface, sheltered from the wind, its dust undisturbed except by the slow thermal convection of the daytime heating cycle. The sun is now approaching its zenith, not directly overhead, because you are in the equatorial region of Mars, and the sun never reaches perfectly overhead except twice a year at the equinoxes, but high enough to cast nearly vertical shadows and to heat the dark basalt of the caldera rim to temperatures approaching 0 degrees Celsius. The stars are not visible now. The sky is the dark, dusty, familiar daytime color of Mars, but deeper here, less orange, more of a brownish purple at the zenith, where the atmospheric column above you is thinnest. If you were to look at the sky directly overhead with appropriate equipment, you would be able to detect individual stars even in the daytime. The atmosphere here is thin enough that the daytime sky does not completely overwhelm the brightness of the nearest stars. You think about the sample tubes in Jezero Crater, far to the east and 21 kilometers below, sitting in their cache sites, sealed, waiting. You think about Ingenuity, tilted on its landing site, 700 meters from the rover that carried it here. Silent now, its rotor blades still, its cameras dark. You think about Insight, on the plains of Elysium, its solar panels coated in dust, its seismometer no longer recording. And you think about Perseverance, still moving, still pressing its wheels into the ancient delta sediment of Jezero Crater, still sending its data upward to the relay orbiters, still recording the composition of the air and the temperature of the ground and the spectral signature of the rocks around it. 110 watts, moving through a world that has been waiting here undisturbed for 4 billion years. The sun begins to descend toward the western horizon. The shadows in the caldera lengthen. The eastern inner wall, lit since morning, begins to cool as the direct sunlight angle drops. The temperature at the caldera rim has peaked and is falling again. In a few hours, it will be night on Olympus Mons, and the caldera will be cold and completely dark, and the stars will appear harder and more numerous than anywhere else on the planet's surface, because here the atmosphere between you and them is thinnest. Standing at the top of the largest mountain in the solar system, under a sky that is almost space, the dust moves in a small eddy at the caldera rim. A few particles lift briefly and then settle back to the rock surface. The movement lasts perhaps 3 seconds and then is gone. Everything else is still. The volcanic plain below the escarpment, the Tharsis Plateau, the ancient lava fields, the terrain you crossed in the dark, is invisible from here, curved below the horizon. The canyon is invisible. The crater is invisible. The sample tubes are invisible. All the evidence of human presence on this planet, the rovers, the landers, the impact sites of spent spacecraft, the footprint-like patterns of wheel treads pressed into the ancient dust, all of it is invisible from this height, too small, too far, too thoroughly swallowed by the scale of the world you are standing on. Mars does not know you are here. It has not registered the presence of the machines, the signals, the sample tubes, the 30 square kilometers of touched surface on a world with 144 million square kilometers of it. It has not changed in any measurable way. The dust still moves. The temperature still cycles. The sun still rises in the east and crosses the sky in a single Martian sol and sets in the west, and the thin atmosphere still carries its iron oxide dust from one hemisphere to the other, and the ancient riverbeds still record the direction of water that stopped flowing billions of years before the first human looked up at a red point of light in the night sky and wondered what it was. The shadows in the caldera are long now. The sun is lower. The sky at the western horizon is beginning its transition toward the brief, strange blue of Martian twilight. And somewhere to the east, where the canyon cuts 4,000 kilometers across the surface, and the ancient delta preserves its layered record, and the machine moves on its wheels through the dust, somewhere out there, the answers to the oldest questions are sitting in the ground, waiting as they have always waited, quietly, in the dark. The night comes faster here than at lower elevations. Not because the planet rotates more quickly at altitude, it does not, the rotation is the same everywhere, but because the thin air at the summit of Olympus Mons holds the last light of day for a shorter time. On the plains below, suspended dust scatters the final sunlight for 30 or 40 minutes after sunset. Here, above most of that dust, the transition is quicker. The sun drops below the western horizon, and within 15 minutes the sky is dark. The stars appear. There are approximately 5,000 stars visible to the naked human eye from the surface of Earth on a clear night far from city lights. From the summit of Olympus Mons, above most of the Martian atmosphere, the number of visible stars is significantly higher, perhaps 8,000 or more, because the sky here is darker and the atmosphere between the observer and the stars is thinner and scatters less light. The stars do not twinkle here the way they do from Earth, because twinkling, scintillation, is caused by turbulence in the atmosphere bending the light irregularly as it passes through. With almost no atmosphere above you, there is almost no turbulence. The stars are steady, hard, precise. The Milky Way is not a diffuse band here. It is resolved at its brightest sections into individual stars layered behind individual stars, layered behind more stars. The depth of the galaxy visible in a way it rarely is from any point on Earth's surface. The dark lanes in the Milky Way, regions where clouds of dust and gas block the light of the stars behind them, are deep and well defined. The galactic center in the direction of Sagittarius is a dense brightness that on Earth is washed out by humidity and atmospheric scatter and the cumulative glow of cities hundreds of kilometers away. Here it is simply bright, a dense concentration of light with structure, with gradient, with the visible shape of a galaxy seen edge on from a point 2/3 of the way out from its center. You are looking at the Milky Way from Mars. The thought does not resolve itself into anything simple. It sits with you the way large numbers sit with you, present, real, incompletely held. To the east, the planet curves away below you. The haze layer, the main dust-bearing layer of the Martian atmosphere, which extends from the surface to perhaps 30 or 40 kilometers altitude, is visible from this elevation as a thin, faintly luminous band near the horizon, backlit by the last traces of twilight. Above it, the sky is black. Below it, the surface of Mars extends into the darkness, invisible but present, 4 billion years of geological record lying quiet under the stars. The global dust storm season on Mars runs roughly from the southern hemisphere spring through summer, approximately the period when Mars is closest to the Sun in its elliptical orbit. The orbit of Mars is more eccentric than Earth's. At its closest approach to the Sun, Mars is about 206 million kilometers away, and at its farthest, about 249 million kilometers. That difference, roughly 20%, means Mars receives about 45% more solar energy at perihelion than at aphelion. The increased solar heating at perihelion drives stronger atmospheric convection, stronger winds, and a higher probability of regional dust storms growing into planet-encircling events. During a global dust storm, the optical depth of the Martian atmosphere, a measure of how much light is blocked by suspended particles, can rise from a typical clear sky value of about 0.5 to values above 5 or even 10. An optical depth of 5 means that sunlight reaching the surface has been reduced to less than 1% of its clear sky value. The sky during a global dust storm on Mars is not simply orange, it is a deep opaque ochre, the color of a world wrapped in its own ground. The surface material lifted into the air and spread across the entire planet in a self-sustaining cycle of heating and wind that can persist for weeks or months before the dust finally settles. From the summit of Olympus Mons, a global dust storm would appear different than from the surface below. The summit extends above the main dust-bearing layer. During a significant global storm, the dust haze would be visible below as a thick orange-brown layer wrapping the entire visible surface of the planet, while above it, the sky would remain relatively clear, dark, cold, nearly free of suspended particles. You would be looking down at the storm from above, the way a passenger in an aircraft looks down at a layer of cloud, and the planet below would be invisible, swallowed by its own weather. Tonight there is no storm. The dust haze layer at the horizon glows faintly with the last of the twilight, and above it the stars are clear, and the caldera below you is cold and dark and silent. The temperature at the rim is dropping through -70 degrees Celsius and continuing downward. The basalt beneath your feet is contracting almost imperceptibly as it cools, the thermal stress working slowly through the rock, continuing the patient process of fracturing that has been crumbling the edges of this caldera for millions of years. In some millions of years, the caldera rim will look different. Pieces of it will have fallen inward. New landslide scars will have formed on the inner walls. The overall shape, the gentle dome of the volcano, the circular escarpment, the nested calderas at the summit, will be recognizable, but the details will be different, worn by time in the way that all things are worn by time, even on a world this cold and this dry and this quiet. But that is millions of years from now. Tonight the caldera rim is as it is. The stars are as they are. The dust moves in its slow planetary circulation. Perseverance is moving across the delta of an ancient river on the far side of the planet, pressing its wheels into dust that has been still for longer than there have been animals on Earth. The dark deepens. The temperature continues to fall, and Mars turns, slowly, under its thin, cold sky, carrying all of this, the mountain, the canyon, the crater, the machine, the sealed tubes, the tilted helicopter, the silent lander, carrying all of it around the sun at 24 kilometers per second in an orbit that takes 687 Earth days to complete, in a solar system 4.5 billion years old, in a galaxy 100,000 light years across, in a universe whose age and size exceeds any number the mind was built to hold. The dust never fully settles on Mars. Even on the quietest days, days with no detectable wind, no passing dust devils, no regional storm building in the southern basin, individual particles remain suspended in the Martian atmosphere indefinitely. They are too light to fall. The force of gravity on Mars is 38% of Earth's, and the particles themselves are so fine that the weak gravitational pull is insufficient to overcome the aerodynamic drag of even the thin Martian air against a particle only a fraction of a micrometer across. They simply stay up, they circulate, they move with the global atmospheric flow, carried from the southern hemisphere to the northern hemisphere and back again in a cycle tied to the seasons, to the orbital position of Mars around the Sun, to the temperature gradients between the polar ice caps and the equatorial plains. This is the background state of the Martian atmosphere. This is what the sky looks like on a calm day. Not clear, not blue, a persistent diffuse haze of suspended iron oxide particles, uniformly distributed across the planet, responsible for the orange color that has been visible from Earth for as long as human eyes have looked at the sky. The dust is not passive, it is a driver of the climate. Suspended dust particles absorb solar radiation and re-emit it as infrared heat, warming the atmosphere directly. This warming changes the temperature gradients that drive atmospheric circulation, which moves more dust, which changes the temperature gradients further. The dust and the atmosphere are coupled in a feedback system that, under the right conditions, becomes self-amplifying. A regional storm lifts more dust. More dust warms the atmosphere. Warmer atmosphere drives stronger winds. Stronger winds lift more dust. The cycle, once started, can continue for weeks or months before the dust loading becomes high enough that the surface below is so shielded from solar heating that the temperature gradient driving the winds finally collapses. This is how a planet wraps itself in its own ground. What makes the timing of any global storm impossible to predict with certainty is that the threshold between a regional event and a planetary one is not a fixed line. It depends on the state of the atmosphere at the moment, how much dust is already suspended, how strong the existing temperature gradients are, whether the initial lifting event happens in a location with the right geometry to amplify rather than dissipate. Scientists have cataloged every global storm observed since orbital monitoring began in the 1970s, and they still cannot say with confidence when a regional storm begins whether it will stay regional or consume the planet. The data accumulates, the models improve, the uncertainty remains. You are descending from Olympus Mons now, moving back down through the elevation gradient, back into the lower atmosphere where the dust haze thickens around you as you descend. The escarpment passes below you. The volcanic plains of Tharsis extend to the south and east. The light is the early morning light of a new Martian soul. The sun has been up for perhaps 3 hours. The shadows still long, the rocks still cool from the night before. The dust beginning its daily cycle of lifting and settling as the surface temperature climbs toward its afternoon peak. The dust haze is slightly thicker today than yesterday. Not dramatically, you would not notice it without instruments, but META on Perseverance, 4,000 kilometers to the east, has recorded a slight increase in atmospheric opacity over the past several sols. Somewhere in the southern hemisphere, a regional dust storm has been growing. It is not yet a global event. It may never become one, or it may be the beginning of the storm that covers the planet. No one knows yet. The data is still coming in. The Martian dust has properties that make it unlike any dust encountered on Earth. It is not simply pulverized rock. Over 4 billion years of ultraviolet irradiation, the surface minerals of Mars have been chemically altered in ways that produce a dust with unusual electromagnetic properties. The particles carry electrostatic charge, generated both by the ultraviolet radiation knocking electrons loose from mineral surfaces and by the triboelectric charging that occurs when particles collide with each other during transport. This charge causes the dust to adhere to surfaces with a tenacity that surprised early mission planners. It clings to camera lenses, to solar panels, to the smooth surfaces of rover wheels, to anything it contacts. Removing it is difficult. On Earth, a damp cloth would solve the problem. On Mars, there is no moisture, and any mechanical attempt to clear dust risks damaging sensitive surfaces. The Phoenix lander, which operated in the Martian Arctic in 2008, discovered that the Martian soil beneath the surface contained ice, water ice, present just a few centimeters below the surface at high latitudes. When Phoenix's robotic arms scraped the soil and exposed the ice, the white patches were visible in the lander's cameras. Within 4 Martian days, those patches had disappeared, not melted but sublimated, converted directly from solid ice to water vapor by the low atmospheric pressure, which does not allow liquid water to exist at the surface under most conditions. The water vapor entered the atmosphere and was carried away by the circulation. This is the water cycle of Mars. Not rain, not rivers, not liquid pools. A slow sublimation of ice directly into vapor, transport across thousands of kilometers in the atmosphere, deposition as frost on cold surfaces, sublimation again. The total amount of water cycled through the Martian atmosphere in a year is small, the equivalent of a layer a fraction of a millimeter deep spread across the entire planet, but it has been operating continuously for billions of years, and it has shaped the polar ice caps, the permafrost at high latitudes, and the chemistry of the surface soil everywhere on the planet. The polar ice caps of Mars are not purely water ice. The North Polar Cap is predominantly water ice, overlaid by a seasonal cap of carbon dioxide frost that forms each winter and sublimes each spring. The South Polar Cap is more complex. It contains a permanent residual cap of carbon dioxide ice overlying water ice, the only place in the solar system outside of comets where solid carbon dioxide exists naturally on a surface in thermal equilibrium with the atmosphere. The South Polar Residual Cap is approximately 8 kilometers across and roughly 8 meters thick in its carbon dioxide layer. Beneath it, the water ice extends much deeper. Estimates suggest the total water ice in both polar caps, if melted and spread uniformly across the planet, would form a global ocean between 22 and 33 meters deep. Mars is not a dry world, it is a cold world. Its water is locked in ice, in permafrost, possibly in subsurface liquid reservoirs. The dryness at the surface is a consequence of the temperature and pressure conditions that have prevailed for perhaps 3 billion years since the planet lost most of its atmosphere to the solar wind following the collapse of its global magnetic field. 3 billion years ago, when Mars still had a thicker atmosphere and liquid water on its surface, the world you are walking through would have been unrecognizable. The plains of Tharsis, currently the driest, coldest, most geologically active-looking terrain on Mars, would have had, at various points in the planet's early history, volcanic eruptions adding massive quantities of water vapor and carbon dioxide and sulfur dioxide to a thicker atmosphere, generating acid rain that fell on the volcanic rock and chemically weathered it, generating the sulfate minerals that Opportunity and other rovers have found across broad regions of Mars. The atmosphere was thick enough, early in Mars's history, to support a greenhouse effect that kept the planet warm enough for liquid water to exist at the surface. Not permanently everywhere, not in the way Earth has liquid water, but episodically, in warm periods, in seasons, in years when volcanic outgassing added enough greenhouse gas to tip the climate into a temporarily warmer state. The evidence for this is written in the rocks. Phyllosilicates, clay minerals that form only in the presence of liquid water, have been detected from orbit across broad regions of the ancient southern highlands, regions more than 3 billion years old. Carbonates, which form when carbon dioxide dissolves in water and precipitates as solid mineral, have been found in Jezero Crater and elsewhere. Sulfates, formed when sulfur dioxide from volcanic emissions dissolved in water, are found in layered deposits exposed by erosion across the Meridiani Planum and other ancient terrains. Each mineral type carries information about the water chemistry and temperature conditions under which it formed. Phyllosilicates suggest neutral to slightly alkaline water. Sulfates suggest more acidic conditions. The transition between phyllosilicate-bearing and sulfate-bearing terrain in Mars's geological record is interpreted as a shift in climate from an earlier period of wetter, more neutral conditions to a later period of volcanic acidification, followed by the progressive drying that eventually produced the Mars that exists today. A planet that was once something else entirely, changed so slowly that no single moment marked the transition. The dust around your feet on the Tharsis Plains is the final product of all those transitions. The iron oxide particles you are walking through contain iron that was once dissolved in ancient water, precipitated in ancient lakes, incorporated into ancient rock, weathered and re-weathered over billions of years until it reached this form, this fine red powder, suspended perpetually in the atmosphere, coating everything, defining the color of a world as seen from the surface of another world. You look east, the direction of Jezero, the direction of the delta and the sample tubes in the rover, the direction of the ancient river that is long gone and the lake that is long dry and the chemistry that is still sitting in the rock, waiting for the instruments that can read it properly. The haze thickens slightly as you watch. It is not a storm, not yet. It is a slight increase in the suspended dust load, a regional perturbation in the atmospheric circulation, perhaps a large dust devil field developing somewhere to the south, perhaps the leading edge of the regional storm that META has been tracking. The effect on visible light is subtle. The sky is a slightly richer orange, the shadows slightly softer, the distant horizon slightly more obscured. The sun is still visible as a distinct bright disk, not yet diffused by heavy dust loading into the smeared, directionless glow of a major storm. But the change is there. On Mars, changes in atmospheric opacity are measured continuously by the rover's instruments, by the orbiters above, by the spectroscopic observations of ground-based telescopes on Earth that can detect the integrated dust loading of the atmosphere from the light reflected by the planet's disk. The monitoring is continuous because the consequences of a major dust storm for surface operations are severe. If a global storm develops, solar-powered surface assets lose power. If a global storm develops during a period when a crewed mission were on the surface, a future scenario, one that mission planners are already designing around, the crew would need to shelter, to conserve power, to wait out the storm in a habitat with its own power supply, watching through windows as the sky turned the deep opaque ochre of a world in the grip of its own weather. The current dust loading is manageable. Perseverance continues to operate, Its radioisotope power source does not care about the optical depth of the atmosphere. It generates its 110 watts, whether the sky is clear or opaque, whether it is day or night, whether there is a regional storm or a global one. This is one of the reasons nuclear power was chosen for perseverance over the solar arrays that powered earlier rovers. The hard lesson of Opportunity's death in the 2018 storm was built into the design of its successor. The haze continues its slow thickening around you. The sun is now a slightly softer disk, its edges less sharp than they were at dawn, its color slightly more orange than the clear morning white it had at the start of the day. The temperature at the surface is still rising. Peak temperature on Tharsis is still hours away, but the rate of warming is slightly slower than it would be on a clearer day. The dust is intercepting some of the solar radiation before it reaches the surface. This is the dual nature of Martian dust. It warms the atmosphere while cooling the surface. It circulates the climate while smothering it. It preserves the ancient surface record while slowly, grain by grain, reworking it. It is simultaneously the most destructive and the most preserving force on the planet. Destructive to the machinery of exploration, preserving to the geological record that exploration seeks to read. You stand on the Tharsis plain and watch the sky change. It is a quiet change. There is no drama in it, no visible clouds building, no darkening that progresses quickly, no wind that rises to a howl, just a gradual deepening of the orange, a gradual softening of the shadows, a gradual narrowing of the visible horizon as the haze thickens imperceptibly with each passing hour. Mars changes slowly. Most of the changes that have defined this world happened on timescales of millions to billions of years. Even the dust storms, dramatic by Martian standards, take days to weeks to develop and months to fully clear. Patience is the fundamental condition of this world. The orbital mechanics of Mars make its seasons different from Earth's in a way that amplifies this. Mars's axial tilt is 25.2 degrees, close to Earth's 23.5 degrees, which means it has seasons driven by the same tilt-driven change in solar angle. But Mars's orbit is more elliptical than Earth's, and the two effects, axial tilt and orbital distance, are not synchronized the same way they are on Earth. In the current Martian epoch, the southern hemisphere summer coincides with Mars being closest to the sun, which makes southern summers hotter and shorter than northern summers, and southern winters colder and longer than northern winters. This asymmetry is one reason the South Polar Cap retains its carbon dioxide ice year-round, while the North Polar seasonal cap of carbon dioxide completely sublimes each spring. Over long timescales, tens of thousands to millions of years, Mars's axial tilt varies much more widely than Earth's. Earth's tilt is stabilized by the gravitational influence of its large moon, which damps the variations to a range of roughly 22 to 24.5 degrees over a 41,000-year cycle. Mars has no large moon. Phobos and Deimos are too small to stabilize the axial tilt, and without that stabilization, Mars's tilt has varied over geological time between 0 degrees and perhaps 60 degrees or more, driven by the gravitational perturbations of Jupiter and the other outer planets. During periods of high axial tilt, the polar regions of Mars receive intense seasonal sunlight that sublimes large quantities of ice, thickening the atmosphere, potentially warming the climate enough for liquid water to exist transiently. During periods of low axial tilt, the poles receive less sunlight, ice accumulates, and the atmosphere thins further. This means the Mars you are standing on is not the only Mars that has existed. It is one configuration among many, one point in a long, irregular oscillation of climate states that has been ongoing since the planet formed. The current thin atmosphere, ice-locked state, is not a permanent condition. It is a phase. The next phase, whatever it will be, is determined by physics, by orbital mechanics, by the gravitational interactions of objects billions of kilometers away, and it will arrive on timescales so long that the entire span of human civilization would register as a single moment within it. The future of this world is already written in its orbital equations, unfolding on a clock no human life can witness. The dust haze around you has stabilized. The regional storm to the south has not grown, at least not in the last several hours. The sky remains a consistent orange, the sun a consistent soft disk, the shadows consistent and present. The Martian afternoon is deepening toward its long, slow approach to evening. The temperature at the surface has peaked and is beginning its descent toward the overnight low. You stop walking. You stand on the volcanic plain of Tharsis, and you are still. The dust at your feet does not move. The wind has dropped to nearly nothing in the midday lull, a regular feature of the Martian diurnal cycle, when the temperature gradients that drive morning and evening winds are temporarily equalized by the peak heating of the afternoon. In this stillness, the Martian surface is as close to absolute quiet as it ever gets. The entire planet is here, not visible. Most of it is beyond the horizon, curving away below the limit of your sight, but present. 4,000 kilometers to the east, the canyon, another 4,000 beyond that, and beyond the horizon entirely, the ancient cratered highlands of the southern hemisphere, older than any surface on Earth, their craters so densely packed that the landscape between them is itself mostly ejecta from ancient impacts. To the north, the plains of Vastitas Borealis, the low, flat, ancient ocean floor of the northern hemisphere, covered in a thin layer of sediment, its basaltic crust buried under billions of years of dust and volcanic resurfacing. To the south, the polar ice cap, carbon dioxide and water ice, stacked in annual layers, each layer thinner or thicker depending on the climate conditions of the Mars year in which it was deposited. The whole stack a detailed record of Martian climate going back millions of years. And beneath all of it, beneath the dust, beneath the regolith, beneath the fractured basalt and the ancient sedimentary layers and the deep volcanic crust, the mantle, still warm, still slowly cooling, still carrying within it the heat of formation, the residual energy of the radioactive decay of potassium and uranium and thorium in the deep rock, energy that has been diffusing outward through the planet for 4.5 billion years and will continue to diffuse for billions more, growing weaker with each passing epoch, the planet cooling degree by imperceptible degree toward the cold equilibrium temperature of interplanetary space. Mars is alive in the only way a rocky planet can be alive. It is changing, it is cooling, it is cycling its volatiles between surface and atmosphere, it is recording. Every wind that moves a grain of dust records something. Every temperature cycle that cracks a rock records something. Every cosmic ray that strikes the surface, every ultraviolet photon that breaks a chemical bond, every Marsquake that sends seismic waves through the crust, all of it is information written into the physical state of the planet, preserved in the cold and the dryness, waiting to be read. Perseverance is reading some of it. The scientists whose data it sends back are reading some of it. And the answers, when they come, if they come, will be answers not just about Mars, but about the conditions under which life can begin, and what happens to a world when those conditions change, and whether the chemistry of life is robust enough to survive in the cold and the dark and the thin air of a world that has been dying slowly for 3 billion years. The sun is lower, the shadows are long, the sky is deepening toward the warm, saturated orange of Martian late afternoon. In perhaps 2 hours, the sun will reach the horizon, and the brief blue of twilight will begin. The afternoon wind has returned. This is normal for the Martian diurnal cycle. The midday lull gives way, in the mid-afternoon, to a convective wind driven by the difference in temperature between the heated surface and the cooler air above it. On Earth, this same mechanism drives sea breezes, valley winds, the afternoon thunderstorms of tropical regions. On Mars, without the moderating influence of large bodies of water, without the moisture that fuels convective storms, the afternoon convective wind is dry and dusty and moves at speeds between 5 and 15 meters per second, fast enough to raise fine particles from the surface, not fast enough to move anything larger than dust. The wind moves across the Tharsis Plain from the south, carrying its load of suspended particles, adding them to the existing haze, shifting the optical depth of the atmosphere by small fractions that META records and transmits to Earth with each communication window. The data is accumulating. The atmospheric science team watching it is building a picture of how the regional storm to the south is evolving, whether it is intensifying or weakening, whether the conditions exist for it to grow beyond its current regional extent. This is how Martian meteorology works in practice, not with weather stations on every hilltop. Mars has no hills covered in weather stations, no network of ocean buoys, no fleet of radiosondes launched daily from airports around the planet. It has a handful of instruments on a handful of spacecraft, each one a precise but isolated data point in the vast, undersampled space of Martian atmospheric science. The gaps in the observational network are enormous. A dust storm could initiate in a region of Mars that no orbiter is currently passing over and grow for hours before any instrument detected it. The science of Martian weather is being built from fragmentary evidence, painstakingly assembled over decades of observation, each mission adding a few more data points to a picture that is still far from complete. What the data does show, clearly and consistently, is that Mars is not a static world. It is a world in motion. The dunes of the North Polar region, the vast erg of dark basaltic sand that rings the North Polar ice cap, covering an area roughly the size of Texas, are actively moving. Measurements from orbit have detected dune migration rates of up to 1 meter per year in some locations. The dunes are dark because they are composed primarily of basaltic sand, the same dark volcanic material that makes the Tharsis Plains dark in places where the dust cover is thin. They have been shaped by the katabatic winds that flow outward from the polar ice cap in winter, and by the seasonal sublimation of the carbon dioxide frost that covers them each winter and reveals them each spring, and by the complex interaction between the polar topography and the global atmospheric circulation. These dunes were first photographed from orbit in the 1970s. Decades of subsequent imagery have revealed that they are not static. They are not the frozen relics of an ancient Martian wind regime, preserved in geological amber. They are current. They are moving now in response to winds that are blowing across the Martian surface today, in the same patterns they have been blowing for thousands of years, in the same patterns that will continue for thousands more. Mars is a world with a present, not just a past. The basalt beneath your feet on the Tharsis Plain records a past. The ancient southern highlands record a past even further back. The polar ice caps record a past of climate cycles stretching back millions of years. But the dunes are recording now. The dust suspended in the atmosphere is from now. The temperature measured by META an hour ago is from now. The Marsquake that InSight recorded in 2022, the largest in its operational history, was from now, or near enough to now, in geological terms, to be indistinguishable. The planet is alive with its own physics. It has been since it formed, and it will be long after every machine we have sent to its surface has gone silent. There is a detail about the death of opportunity that the numbers do not fully carry. When engineers at JPL determined that the 2018 storm had silenced the rover, they did not simply send a shutdown command and close the file. They spent 8 months sending over 1,000 recovery attempts across 150 million kilometers of space, each one arriving at a machine that could not answer. The transmissions went out anyway. On February 13, 2019, the final command was sent. The team included in that last transmission a recording of a song, Billie Holiday's "I'll Be Seeing You." The rover did not respond. It never would. What that detail reveals is something the mission statistics do not, that the people who built these machines and guided them across another world for 15 years do not experience their silence as a technical outcome. They experience it the way anyone experiences a loss that was always coming but arrived before it was welcome. The rover was a machine. It did not know the song was sent, but the song was sent anyway, into the dark, across 150 million kilometers, to a machine that had gone silent in a storm on a cold, rust-colored world that no human being has ever touched. The dust that silenced opportunity is the same dust now drifting across your feet on the Tharsis Plain, the same particle size, the same iron oxide chemistry, the same electrostatic charge that makes it cling to everything it contacts. It is the universal solvent of Mars, not in the chemical sense, but in the practical sense. Given enough time, it covers everything. It covered Pathfinder. It covered Phoenix. It covered Insight. It will eventually cover Perseverance. It will cover any habitat or equipment that a future human crew leaves on the surface. It is patient in a way that nothing biological can be, because it is not waiting. It is simply accumulating, the way Mars accumulates everything, slowly, completely, without urgency. Everything here is covered, eventually. Everything here is preserved, eventually. There is no difference between the two. The wind on the Tharsis Plain is moving slightly faster now. The afternoon convection is at its daily peak. The temperature gradient between the sun-heated surface and the atmospheric column above at its maximum. Fine dust lifts from the open patches between the darker basalt exposures and swirls briefly before settling again a few meters downwind. The overall dust loading of the atmosphere is still manageable, still a clear enough sky to see the sun as a disk, still enough light to cast shadows, but the trend of the day has been toward thicker haze, and the trend of the season is toward increased storm probability. You watch a small dust devil form perhaps 500 meters to your east. It begins as a barely visible swirl at ground level, a tightening of the dust movement that signals the development of a convective vortex. The Coriolis effect on Mars, though weaker than on Earth due to the slightly longer day, still imparts a rotation to large enough convective columns, and within 30 seconds of its initiation, the dust devil has organized into a visible rotating column, perhaps 30 meters wide at the base and already climbing toward 100 meters in height. The walls of the vortex are visible as a darkening of the air where the dust concentration is highest, a thin shell of spinning, lifting particles surrounding a relatively clear eye. Inside the eye of a dust devil, the pressure drops slightly, not dramatically, a few pascals at most in a Martian dust devil, but measurably. If META were nearby, it would record the pressure signature as the dust devil passed over the rover. During its 4 years of operation, InSight logged hundreds of such pressure drops from vortices crossing the plains of Elysium, brief, faint signals in the barometric record, each one the trace of a spinning column of dust that formed and dissolved within minutes. The dust devil climbs to 300 meters, 400. The upper section begins to lean with the prevailing wind, the top moving slightly faster than the base, stretching the column into a slight tilt. At 500 meters, the column begins to weaken. The surface heating that drives it is no longer sufficient to maintain the temperature gradient needed to sustain the updraft at that height. The dust devil starts to dissipate from the top down, the upper section dissolving into the general haze, while the lower section continues to spin for another minute before it too relaxes back into the background wind and the lifted dust disperses. The whole event lasted less than 3 minutes. The dust it lifted will remain suspended for hours. Some of it will travel tens of kilometers before settling. Some of it will be carried to higher altitudes by the afternoon convective mixing and remain suspended for days. Each dust devil, each gust of wind, each regional storm is a small redistribution of material, a rearrangement of the surface, a mixing of the atmosphere, a continuation of the slow planetary scale sorting of material that has been ongoing since Mars first had an atmosphere to move things around in. You are watching a planet sort itself, on a timescale too slow to perceive directly, but real enough to measure. You have been on Mars for a long time now. You have stood in an ancient lakebed and read the layers of a river that died before the first animal moved on Earth. You have watched a dust devil form and dissolve on the crater floor. You have crossed the volcanic plain in the dark, under a sky full of hard, steady stars, toward the edge of a canyon that has no equal in the solar system. You have stood at the rim and looked down into a darkness 7 kilometers deep. You have walked the gentle, barely perceptible slope of the largest mountain in the solar system and stood at its summit above most of the planet's atmosphere, looking out at a sky almost indistinguishable from space. You have watched the dust move. You have felt, or imagined feeling, the temperature drop at the end of each sol, the slow release of stored heat from the rock as the sun descends, the gradual approach of the Martian night with its extraordinary stars and its extraordinary cold and its extraordinary quiet. And all of it, every measurement, every observation, every data point that gives this world its detail, was gathered by machines the size of cars and helicopters and toasters, built by people on a small blue planet 200 million kilometers away, sent across interplanetary space on trajectories calculated years in advance, landed with precision on a world where no correction could arrive in time to matter, operating in conditions that would destroy them without the careful engineering layered into every component. The dust, the cold, the radiation, the thin air, the communication delay, the months of transit, the 7 minutes of terror during atmospheric entry, all of it navigated, all of it survived, so that this geological record, this chemical library, this ancient preserved history of a world that was once something else entirely, could be read. We sent our eyes here because we could not come ourselves. Not yet. The sun touches the western horizon. The sky near the sun begins to change. The deep orange of the Martian afternoon day bleeds into something richer, more saturated, as the dust near the horizon catches the oblique low-angle sunlight and scatters it into a band of warm color running along the western horizon. Above that band, the sky grades upward through progressively darker shades of orange and brown into the deep dusty purple of the upper atmosphere, and above that into the first darkness of the coming night. And then, for a few minutes, blue. It appears near the sun, a cold, deep, unexpected blue in the sky within 15 or 20 degrees of the setting disk. The same dust that makes the daytime sky orange, now scattering the low-angle light in a way that preferentially passes blue wavelengths toward your eyes. The blue deepens as the sun drops below the horizon. It lingers, spreading slightly, a fan of blue-gray in the western sky, while the rest of the sky continues to darken through orange and purple and into black. Then it fades. Within 20 minutes of sunset, the blue is gone. The sky is uniform dark. The first stars are appearing, and the surface of Mars has already dropped several degrees below its afternoon peak. The Milky Way is emerging from the darkening sky, not gradually but quickly, the thin atmosphere surrendering its brightness as the last scattered twilight light dissipates. The stars are the same stars that are visible from Earth, the same constellations, though from Mars the constellations look slightly different because the angle of view has changed by the distance between Earth's orbit and Mars's orbit, and the nearest stars have shifted their apparent positions relative to the distant background stars by a tiny but measurable amount. From Mars, the nearest stars, Alpha Centauri, Barnard's star, the stars of the Centaurus region, have shifted by fractions of a degree, not enough to change the shape of a constellation perceptibly, but enough to be measured, enough to be real. From Mars, the sun is a slightly smaller, slightly less warm point of light. From the orbit of Neptune, it would be brighter than any other star but not dominant. From the nearest other star, it would be invisible to the naked eye, and yet, from here, from this cold, dusty, ancient volcanic plain, it is still the most important object in the sky, still the source of all the heat that drives the seasons and the dust storms and the sublimation of the polar caps and the photochemistry of the thin atmosphere, still the clock around which this planet has been orbiting faithfully for 4.5 billion years. The night deepens. The temperature at the surface passes through -50, -60. The rock beneath you is cold to the touch, the heat of the day entirely gone, the basalt conducting the last of its warmth outward into the air in a process that will continue all night long, the temperature falling until just before dawn, when the residual heat from the day before is nearly exhausted and the surface reaches its overnight minimum, and then very slowly begins to warm again as the first light of the next sol appears at the eastern horizon. This cycle has been repeating for 4 billion years. Every sol since Mars had a surface. The sun rises, the temperature climbs, the dust lifts, the convection begins, the temperature peaks, the convection slows, the sun sets, the temperature falls, the dust settles slightly, the stars appear, the temperature continues to fall. The ice deposits from the atmosphere onto cold surfaces in micron-thin layers. and then the sun rises again. 4 billion years, every sol. You are standing in the middle of it, not as an interruption of it, not as something that changes it, but as a witness, a temporary, impossible, brief witness to something that does not need to be witnessed to continue. The planet was here before anything looked at it from the surface. It will be here long after the machines stop working and the signals stop coming, and the last data is downloaded and analyzed and published, and slowly, over centuries, becomes part of the accumulated scientific understanding of a civilization that may or may not still exist in forms we would recognize. Mars does not need us to be here, but we came anyway. And we are still here, in a way, in the instruments and the wheels, and the sealed tubes, and the tilted helicopter, and the quiet lander on the Arctic plain, still here, still listening, still reading the record of a world that has been writing it for longer than there has been anyone to read. The stars turn overhead. Phobos crosses the sky in its fast westward arc, rising in the east, moving against the rotation of the planet, setting in the west, a small irregular moon completing its orbit in 7 hours and 39 minutes. Its surface pitted and gray, its slow inward spiral continuing, its future written in the orbital mechanics of a body too close to a planet's gravity well to escape. The caldera of Olympus Mons is dark, the rim of Valles Marineris is dark, the floor of Jezero Crater is dark, and the sample tubes sitting in the dark are perfectly still, their contents unchanged, their seals intact, their waiting continuing without urgency because there is no urgency in geological time. Perseverance has stopped for the night. It does this every sol. When the temperature drops below a certain threshold, the rover enters a low-power state, conserving the heat generated by its radioisotope system, running only the minimal systems needed to maintain its electronics above their operational temperature limits. Its cameras are dark, its wheels are still, its arm is folded. The tread marks it left today in the delta sediment are already cooling, the dust at their edges settling back very slightly, the ambient temperature contracting the rock around them. It will wake again when the temperature rises enough, when the sun has been up for a few hours and the thermal environment is within operational parameters. Its computers will run their daily diagnostic checks. Its instruments will begin their measurements. Its cameras will open to whatever section of the ancient delta it has driven to overnight, and the day will begin again. But for now, it rests. For now, everything on Mars rests. The planet turns, the stars track their arcs, the dust floats, suspended, the way it always floats, the way it has floated since before the first fossil was laid down in the sedimentary rock of Earth's first oceans. The cold is absolute in the way that only the cold of a world without an ocean can be absolute, deep, immediate, final. And the universe continues its expansion at 67 kilometers per second per megaparsec, every point in space moving away from every other point, the galaxies receding, the cosmic microwave background cooling by fractions of a degree per billion years, a great slow drift of everything away from everything else continuing in silence and in darkness and in perfect indifference to the small, cold, rust-colored world that one small civilization has been learning to read. You are still here, on the volcanic plain, under the stars, breathing the cold, or not breathing it because the air here would kill you in minutes, but feeling it in the way that knowledge becomes feeling when it settles deep enough, when the numbers stop being numbers and start being real. The dust at your feet moves almost imperceptibly. A particle lifts, drifts 3 centimeters on a breath of air so thin it barely registers as a fluid, settles again. Another particle follows. The process is continuous, infinitely patient, driven by the same physics that governs every gas and every solid surface in every atmosphere in the solar system. The particle settles. The surface is still. The stars turn. The night continues and the cold deepens, and Mars turns slowly toward its next dawn in a silence that has been here for 4 billion years and will be here for 4 billion more, deep and old and perfectly, completely real. If you are still awake, there is no need to be. The planet is here. The machines are working. The data is coming in. The answers, if they exist, are being found. You can let go now. The surface of Mars extends in every direction around you. The ancient volcanic rock, the drifting dust, the sealed sample tubes, the quiet rover, the canyon in the dark, the mountain above the atmosphere. All of it present, all of it real, all of it here whether you are watching or not. The stars are overhead. The cold is deep, and the next sol is already coming. If you have been finding your way to sleep to the science of this world, please consider subscribing to Quiet Science at Bedtime. It helps more than you know, and there are many more worlds waiting. Good night. Everything you heard tonight is real. Mars is out there right now.